Um, so, okay, so let's start. So this is a week 4, and today we will be covering a perceptron, followed by the backpropagation algorithm, and then a simple 2 hidden layer neural network implementation in PyTorch. Starting with perceptron. Okay. So perceptron is the building block of neural networks. Here's a simple diagram representing a perceptron. So suppose the input is n-dimensional and each input is represented by these n elements in a vector form. So it's x1, x2 up to xn. And given this input, the output y is simply a label between 0 and 1. So it's a binary classification problem where the input is n-dimensional and the output is going to be one of the two classes, either 0 or the 1. So the idea of perceptron is that all these inputs, we will take the weighted sum of the inputs, add a bias to it, and that will be the g of x. And then we will apply a threshold on this output to get the actual label by. So it means that x1 will be given some weight w1, and these are the weights which we will be learning. So w1, w2, and wn are the weights which are supposed to be learned depending on the input data x and y. So for any input data x, the g of x will be computed as w1 x1 plus w2 x2 plus up to wn xn plus some bias term here p, which is constant, but this is again to be learned during the training process. And once we have this g of x here, we will be using a threshold theta, which will be used to decide the label, the output label of this input x. So if the value of this g of x is greater than some threshold theta, then this model will predict the value 1. If the output of g of x is less than some theta, then the output will be 0. Now, this is dependent on theta, and this is something we have to fine tune. So to remove this, what we will do, we will introduce it itself as a part of the model, and that can be learned. So now we can reshape this inequality or rewrite this inequality as g of x minus theta greater than equal to 0 and g of x minus theta less than 0. So this reduces to nothing but b taking the value of minus theta here, right? This is something which we can equate. And therefore, this can itself be written as 1 dot minus theta, where we can represent 1 as x0. So we are increasing the dimension of the input by by 1 and making that increased dimension value always to be constant 1. Okay, and then to that increased dimension x0, we are adding another weight w0 here. So this bias is nothing but this x0 w0, and this will be the negative of the threshold theta. So initially this threshold theta, we were choosing the threshold, right? Whether so that we assign the label to this g of x, but now this theta is itself the part of the model here, which we can learn through the depending on whatever the data we are giving us. So now g of x becomes I equal to 0 to n wi xi, and please note that here I has started from 0 instead of 1. Okay, and this zeroth term is nothing but x0 w0, where x0 will always be 1 and w0 is something, if we compare with this thresholded model, it is nothing but representing the minus theta here. This is perceptron. Now the next question arises, okay, this is the model, this is the data, this is how the prediction will be done, but how this w is actually being learned? Okay, so these are the w which is being learned depending on the input data, but what should be the procedure to learn it? So moving on to update this. So the idea is that whatever the data is given, assuming it is a binary classification right now, so the idea is that we have to learn a line, if it is a two-dimensional space, or if it is multi-dimensional space greater than 2, then we have to learn certain hyperplane here, which will be trying to divide the input space into these two classes, such that all the points which are lying on one side of the class, one side of this hyperplane, hyperplane is being classified into one class, and the points lying on the other side of the hyperplane are being classified in the another class. So now in this high dimensional space, so this high dimensional space, basically hyperplane is nothing, but when we talk about dimensions more than 2, then line will not make much sense, and therefore we use the notion of hyperplane here. So when we're talking about this hyperplane, so the points which will be lying on this line, okay, those will be the points which will be actually lying on the boundary of these two classes, right? And this, for these points, these W transpose X will be 0. Okay, so these are the points which are lying on the line. And this W, if you try, so now this W is a vector, right? Depending on the dimensionality of the input. So if input is n-dimensional, this W is also n-dimensional. If you look at this diagram here, you will see that the input was x1, x2, up to xn, and so was the W, right? W1, W2, and Wn. So the dimensionality of W and X is exactly same, and there are some high dimensional vectors here. The only difference is that X is given as an input to us, and W is supposed to be learned using this data, such that the error in classifying the input to the true class is minimized. So here this W transpose X equal to 0 represents the set of points X, like so the set of points X for which this equation will be satisfied will be the points lying on this line. And using the definition of the scalar product here, this W transpose X can be written as the norm of W into norm of X into the angle between these two vectors, okay? And let alpha be representing the angle between the vector W and X. And this is 0. So assuming that this neither W is 0 or X is 0, the only possibility for this dot product to be 0 is that alpha has to be 90 degrees. So if this is the line here, which is separating these two classes, then W is nothing but a vector which is perpendicular to this line. Okay, and these are the set of points which are lying on the line. So W is being perpendicular to x3, x2, x1, and so on. Here, these numbers in the superscript are representing the different data points, and the numbers in the subscript will be representing the different elements of the same vector X. Now, okay, so this is the idea of the perceptron, that we have to learn a hyperplane such that it can separate these two classes, and this W will be basically the vector perpendicular to the line, which will be separating these two classifiers. Now, the notion of W is clear. What does W mean here? Moving on to the next step, which is how to update this W. So, suppose there is any input X which belongs to the positive class. So positive class here is that we assume the label by the true label of this input X to be 1. Now in this case, if you see this particular equation, it was being assigned a value of 1 if the output is greater than or equal to 0. So if X is belonging to a positive class, that is the Y has to be 1, then W transpose X should be greater than or equal to 0. Now, if this W is already classifying this new input X correctly, that is, for this input X, this W transpose X is already giving a value of which is positive, then we do not have to change the value of W. But if this W has failed to classify X correctly, then W has to be updated. In that case, what will be the situation? Okay, first let's understand when this W transpose X will be greater than 0. And then we will move to the second case. So now, assuming that this is the data point X, this is the true label, and the model is correctly classified it. So in that case, W transpose X should be greater than or equal to 0, and which can be written as norm of W into norm of X into cos alpha. Alpha is the angle between the vector W and X, to be greater than or equal to 0. Now this norm of W and norm of X will always be positive. This is the definition of the vector norms, right? And now cos alpha is all on which the dimension, the sign of this quantity is depending. So for this to be positive, cos alpha has to be positive, which means alpha has to be less than or equal to 90 degrees. So if you remember, try to remember the cos alpha graph, you will see that cos alpha is positive when alpha is between 0 to 90 degree and negative when alpha is greater than 90 degree. It is also positive when it is minus, it's from 270 to 360 degree, right? So basically the first quadrant and the fourth quadrant, and will be negative when alpha will lie in the second and the third quadrant. So similarly, if X belongs to the other class, that is the negative class in which we are assigning the label true label to be 0, then we expect the W transpose X to be less than 0. That is, the value of the cos alpha should be negative in this case, which means alpha has to be greater than 90 degree. So if this is the hyperplane here and W is the normal to this hyperplane, then all the points which are making an angle of less than 90 degree, basically making an angle between, so this, right? This 90 degree or angle here, which is 270 to 360 degree, will definitely be termed as the members of the class 1 according to this hyperplane. And the data points which are making an angle greater than 90 degree, that is lying in this area, will be classified as the instances of class 0. Now, suppose there comes an input X which is being misclassified by the classifier here. So the classifier is nothing but this W. Give me a second. I just need to add allow setting. Please try to be on time so that it doesn't disturb in middle. Okay. So resuming where we left. So now during the model update, assume that we see a point at time P, which belongs to the positive class, that is the y equal to 1, but the W transpose X of T is less than 0. That is, this hyperplane, which is being represented by W here, has failed to classify X correctly to be classified as a member of class 1. Then W has to be updated, and the procedure should be such that after updating W, let W new represents the updated W. The idea is that W new transpose X should result in a value which is definitely greater than W transpose X. Let's try to look at it diagrammatically. So here is a simple diagram in which the solid line is representing the initial W, and this arrow is representing the direction in which W was pointing, and this is the initial hyperplane. Now there comes this point X of T here, and this W, though it is a positive class point, it has been misclassified by this hyperplane to be a member of class 0. So to classify this point correctly, W has to be updated such that the new hyperplane or the updated hyperplane is able to correctly classify this data point as an instance of class 1. So for that, this hyperplane which is here has to be updated by a certain angle so that this W old is now becomes this W new here, and this xt is getting correctly classified. So what is happening here is that initially this W transpose X, okay, this was the value, right? So this is X, and you take the dot product, that will be negative. And in this case, this W transpose X, when this hyperplane has updated as shown here by this dashed line, this W transpose X will be greater than what it was previously. So the idea here is simple, that the updated W should try to give this dot product value greater than the dot product value which was before updating W. So now if we write this W new, so if you remember the algorithm of the perceptron discussed in lecture slides, the update in W is made as such. So if this is a positive sample X here, we will add X. And if it is a negative sample which was being misclassified, then we will subtract here. Now, since this was a positive example, that is the label was 1 here and it was getting misclassified, we will add X to this. So what will happen now? This W new transpose X of T will become as W plus X of T, because remember, right? This is how W new has been updated. So W new is nothing but the data point, adding it to the initial W. So W plus X of T transpose x of t, which is W transpose x plus L2 norm square of xt. So this is the same value which we had before update, but there is this additional term coming here, right? This will always be positive because this is a norm of a vector. This will always be greater than or equal to 0. Unless if x is not 0, then this will strictly be greater than 0. So now if x is not equal to 0, which we're assuming here to be the case, then what will happen is that adding the norm of this will definitely make sure that this W nu transpose of x is now greater than initial W transpose x, which means that the angle between these two, the angle has decreased. Okay, so let's look at this derivation here. So it means that alpha nu is representing this angle between W nu and x, and alpha is representing the angle between W and x. W is representing the weight parameter before update, and W nu is representing the weight parameter after update. X remains the same in both the cases. So cos alpha nu is nothing, but we can write it as this. That is the dot product of the W nu and x divided by the norm of W nu and norm of x. And this equation here can be written as this equation. So replacing W nu x dot product by dot product of wx and the norm of x square. Sorry. So now this quantity can be written as cos alpha plus this. Okay. So assuming that W is normalized here, that is norm of W is equal to norm of W nu equal to 1, this quantity will represent the cos alpha plus L2 norm of x, which will definitely be positive and greater than 0. So this shows that cos alpha nu is greater than cos alpha, which means alpha nu has to be less than alpha, or now the angle between x and the normal to the line has decreased. That is, the error in misclassifying x has been reduced. So this is a general idea of the perceptron. Now, moving on to backpropagation. So in the lecture, it was covered the neural networks, the feedforward networks, where these perceptrons form the building block of the neural networks. And here, this represents a simple feedforward neural network. It's a 3-layer neural network. The first layer weights are being represented by W1, B1. The second layer weights are being represented by W2 and B2. And the third layer weights represents the W3, B3, where W and B represents the weights and biases of the respective layer. Okay, and this is the input here, x1, x2, and x3. So we are in this example, 3-dimensional input is being considered. The first layer has 3 inputs, 3 hidden neurons, 1 for each element of the input. The second layer has 4 hidden neurons, and the input to each neuron of the second layer is the output of the previous layer. Okay, and so on. Now here D represents the data, the training data, that is x1, y1, x2, y2, xn, yn. So here D is a data set of n distinct points, x1, y1, and this x represents these inputs here, and y is the target label. Let's also assume that the sigmoid represents the activation function to be used. So u1 is equal to sigmoid of w1x plus b1. What it means that x is the input to the neural network. This is the first layer. So the output of this first layer will be that it will be multiplied by the weights, right? So it will be w1x1, w1, so it will be like basically this, the weight of this. So if the weight here is w11, so it will be w11x1 plus w12x2 and so on. Okay, so we can write it in a vector notation as w1x plus bias b1 followed by an activation function, where this activation function can be a sigmoid function, tanh, ReLU, okay, any nonlinear function being used here as an activation function. So this is the u1 is representing the output of layer 1, which will now serve as the input to the layer 2. So for layer 2, the output u2 will be represented as sigmoid of w2 u1 plus b2. Now for layer 3, the output of layer 2 will serve as an input, and its output will be the final output, which we will use for making the prediction. So YP is now written as W3U2 plus P3. So this can also be written as M of X, where M is representing this entire neural network. So M can be seen as a nonlinear function, which is mapping this X to this output YP. Now, so to optimize, to learn these weights, we need some kind of loss function which makes sure that when we are updating these weights, we are able to achieve the target. And this loss function should reflect the target we want to achieve. For example, in case of classification, the loss function will make sure that most of the classes, most of the examples get classified to the correct class. In case of a regression setting, the loss function should aim that the output value should be very close to the true value. So here L is representing this loss function, which is a function of the output of this model M. I'm representing the neural network here. So this is the function of YP and the true label or the value which the network should predict. Now for this example to work, just assume F to be a mean squared error. That is, we're considering a regression setting in which Y is a one-dimensional scalar value. For each input X, we have a scalar value and the network is supposed to predict that scalar value here. So F is a mean squared error of here representing to be a loss function. And then we can represent this loss function L as nothing but 1/2, the norm of L2 norm of square of y1p minus y. So yp is nothing but the predictions made by the network, and y is the true output or the true desired output. And the difference of it has to be minimized. So this loss function ensures that the network prediction should be as close to the ground truth value as possible. Now we have defined here the loss function and a network, and also how this output YP is being computed here. The next step is how to update these W's and B's so that this loss function is minimized. To minimize the loss function, we need to find the value of W for which we can achieve the local minima in this loss function L. Now to reach the local minima, what we can do is we can differentiate this L and can move in the negative of the direction of the gradient. Using this idea, let's start from the last layer. So the last layer represents truth, this layer, okay? Now these are the same equations. We will be using these equations to compute the weights update for these weights update for this network M. So differentiating this loss function with respect to W3 will give the gradient direction of L with respect to W3. And then the update in W3 will be W3 minus a small step in direction of this gradient. So it will be W3 minus eta, where eta is representing the direction, representing a step in that direction, the size of the step. So it will be the final update in W3 should be like W3 minus eta times of day over L by day over W3. So here delta represents the partial derivative. So once we know this partial derivative value, we can easily update the W3. So how to compute this partial derivative? Let's look at what the loss function is. So loss is a function of the predicted value and the true value. And this predicted value is a function of weight W3 and bias W3. So to differentiate L with respect to weight W3, the first L has to be differentiated with respect to YP. And then this YP has to be differentiated with respect to W3. That is the rule of chains. So differentiating L with respect to YP will result in simply YP, 2 being cancelled here with this 1/2. So it will result in a YP, and the derivative of YP with W3 will simply result into U2. Okay, so this is the gradient of L with respect to W3. And to update the W3, it will be basically W3, the value of W3 minus the step size eta, into this value, which is yp into u2. Similarly, the gradient for B3 will be computed as derivative of loss function with respect to yp into the derivative of yp with respect to B3. So derivative of yp with respect to B3 is 1. So this will come as yp. Okay. And therefore, the update for B3 will be B3 minus eta times of yp. This was for last year. The good part here was that the last year was having no activation function here. It was directly being given as an input to the loss function. But what about the second last layer? There is an additional activation function working on this W2U1 plus V2. So for this, we will have one more step in differentiation. Let's look at it. So this is the second last layer. And what it means that now we want to update the weights of the second last layer, which is W2 and P2. So first of all, what has to be done? A simple thing that the derivative of L with respect to W2 has to be computed. So d over L by d over W2 has to be computed. So this is simple, okay? Right? Differentiating L with respect to YP as we did before, and YP with respect to U2 again as we did before. So this is something which we have already done with our last layer. Now what? Now we need to differentiate this U2 with respect to W2. Okay, this is the idea. But if you look here clearly, then it shows that U2 is a function of U1. So this W2 U1 plus P2 is itself a function of U1. Sorry, U2 W2, and then this is further a function of this. Okay, so first of all, this is clear, right? This derivative of L with respect to YP is YP, derivative of YP with respect to U2 is W3. So this will be coming as a multiplier here. The next is this derivative of U2 with respect to derivative of W2. So for that, let's take one step further, and it will be derivative of U2 with respect to derivative of W2. Okay. So what will happen here is that U2 is nothing but the activation function applied on this input, which is W2U1 plus P2. So let's write this as set. So it means that it has to be the derivative of sigmoid functions. First, this function has to be differentiated with respect to this input C, and then the C has to be differentiated with respect to W2. So d over U2 by d over W2 will now be written as sigma prime set dot derivative of set with respect to W2, where sigma prime is representing the derivative of sigma with respect to set. Now this sigma can be any activation function. It can be a sigmoid function, in which case derivative of z, derivative of the sigmoid will be written as e to the power minus z upon 1 plus e to the power minus z square. So simple calculus that it will be minus. So first you approximate this as y and differentiate, then you differentiate this denominator itself, so it will become e to the power minus times of e to the power minus z, and there was again one more minus because of this inverse here. So this whole will become like, this will reduce and simplify to e to the power minus z upon 1 plus e to the power minus z square. Now, in case sigmoid represents the Rey function, which means sigmoid of z is nothing but max of 0, z. In that case, the derivative will be referred as 0 if z is taking a value less than or equal to 0, and the derivative will have a value of 1 if z is greater than 0, and so on. So here, just plug in that value of derivative of sigmoid, that is the activation function, followed by the derivative of z with respect to W2. And what will be the derivative of z with respect to W2? It is nothing but U1. So it will be like sigma prime z into U1. Okay, a simple question. What will be the derivative? Like, what should be the update for B2? Like, how to compute the gradient of loss function with respect to B2? Any idea? Anyone would like to say anything here? So it will be very similar to this W2, but with a minor difference. Okay, so what will happen here is that this table L by table W2 was simplified as this, right? Similarly, derivative of L with respect to B2 will be written as derivative of L with respect to YP into derivative of YP with respect to U2 into derivative of U2 with respect to B2, not W2. Okay, this is the change here. And this will remain the same. So it will be YPW3. But derivative of U2 with respect to B2 will now be written as derivative of the activation function into derivative of Z with respect to B2. And Z is nothing but W2U1 plus B2. So differentiating it with respect to B2 will give a constant 1. So it will be nothing but simply sigmoid prime Z. That is the derivative of the activation function. So the overall gradient of loss function with respect to B2 will be Y3 YP dot W3 dot gradient of the activation function. Okay, so is there any question yet on this perceptron and backpropagation? Okay, okay. So now let's move on to the implementation part. So here is a simple implementation. Okay. In this implementation, we have considered a data set called MNIST. It's a data set of digits which are being written by hand. It's a 28 by 28 images. It looks like this, okay? And this is simply a binary image, either 0 and 1. So this is how it is looking. And there are a total of 60,000 images. So there are 10 classes, class 0, class 1, class 2 up to class 9, and 6,000 images per class. And this 60,000 images forms the training data set. And then there is additional 10,000 images, which forms the test data set. So first, let's look at this data augmentation part. So first look at the data augmentation part. So these are the images, right? These are the original images, 7, 2, 1, 0, 4. So this is how the original images look. Now we can augment these images in multiple ways. The first option is that we can start removing certain patches from this image and make it 1. So which means make it completely black, sorry. So changing its value to 0. So what it means is that here, if you look, let's look at this image of 7, okay? And we start erasing it. So we select a small, okay, maybe look at this 0. Now, in this image of 0, a small patch here has been erased. Can you see it? So this patch has been erased. This is still an image of 0, but on pixel level, it is different from the original image 0 because of this small section here which has been blacked out. So this is one way this image 0 has been augmented to create a similar image, similar looking image, but slightly different from this image. Similarly, the next can be, we can resize it. So this is another image in which the 0 has been enlarged. Okay, this is 0 has been, the size of the 0 has been increased. The other augmentation can be here, in which the 0 has been rotated. So here 0 was aligned with y-axis, but now here the 0 has been rotated and is making certain angle with this x-axis, right? The next option can be, we can blur it. So in this example, the 0 has been blurred. So these are the different ways in which the images can be augmented, like random erasing, random resizing, rotation, blurring, and so on. Let's look at this code, what it is doing. So this data set MNIST is already provided in the PyTorch library. So for this, just import it from torchvision.datasets. Once we get this data set loaded, we can use the set of transforms which are already provided in PyTorch. So these transforms have also been loaded from torchvision.transforms and transforms. And under these transforms, I have shown 4 of these transforms. One is this random erasing, where a small patch of the input image randomly selected and its value is changed to 0. The second augmentation we saw is random Resize Row, in which in this the image is randomly selected, like a small subset or a small patch of the image is randomly selected and is resized to the original size. So the ratio here ranges from 3/4 of the image. So it basically selects that 3/4 of the image and then it resizes it. Okay. Now this random rotation here is that the image is being randomly rotated with any angle theta lying in the range of 0 to 45 degree. Gaussian blur will blur the image. It will use the kernel of size 5, which means 5x5 kernel has been used to blur the image. And the sigma of the Gaussian will be between 0.1 to 2. Now, these are the list of the transformations which will be applied on the images to create different augmentations, the dataset augmentation. So how to apply this transform, and this is how the results are being shown here. So if now let's maybe focus on some another example, maybe look at this example of 5 here. This is the 5. Here the random erasing has not done much change, so it still looks the same. Maybe they selected the patch which was already black, so not any perceivable change is seen. However, when we do this random cropping, then this particular subset of the image was selected and enlarged to fit the original size. So that's why this 5 seems to be enlarged and is slightly cropped here. The next rotation is random rotation, in which this image of 5 has been randomly augmented, rotated by a certain angle less than 45 degree and greater than 0. And this is the image in which the image of 5 has been blurred. So these are the different ways of augmenting their data set during training. And this works as the regularizer for while training the neural networks. Now let's try to create a simple neural network. It will be a feed-forward neural network. There will be 2 hidden layers. The number of neurons in the first hidden layer is 128. The number of neurons in the second hidden layer is 128. And then finally the output layer, which has 10 neurons, 1 per class. Because it's a classification problem here, each image has to be classified into one of the classes between 0 to 9. So this will be the output space here, and this 10 is representing those number of classes here. So how this neural network has been created? The simple structure is that there will be first layer, and the input is 28 cross 28 images, right? So we are just considering right now fully connected layers. So the dimensionality will now be 28 into 28, that becomes 784. So we have this in features here. So the input dimension is 784 for the first layer, and the output dimensionality of this layer will be 128. For the second fully connected layer, it will be 128 as the input, and the output is also 128. And the last layer will take an input of dimensionality 128 and will result in an output of 10 dimensions. Yes, and that is the size of these images in the MNIST dataset. Yes, this is a grayscale image, so there is no channels here. So it's okay. So size means that each image of this dataset. So basically, these are like if you see here. So these are how many images? 4, 6, 8, 10, 12, 14. Yeah. So these are 16 images. So I just put it like this. Maybe what I can do to show you, I can add some spacing here, and then you can see it maybe. Okay. Yes. Yes. So while each image will be inputted as this. So what? Yes. So we are now talking about images, and that image can be an image of any digit because the neural network does, right? Yes, each image is 28 by 28 pixels. So for, yes, right. And yes, yes. Yes, that is always possible, right? So here, if you look at this look at this network, the input dimensionality is 784, right? The first layer is the one which is interacting with the input, but the dimensionality of the hidden dimensionality is 128, right? You can make it anything. Uh, but then you have to be consistent with the output of this and the input of the next layer. Okay. And with respect to dataset, only this value is fixed, which is the input dimensionality here, and the output dimensionality here. Okay, so the rest is up to us. The only constraint is that these two values should match. Okay, so I can even change it maybe to make it more clear. So let's change it to 64 here. Then I have to change 64 here as well. Okay, because the output of this will be the input to the FC3. Okay, so now the network has changed. Okay, now if you want to see how many parameters are there, we can also do that. So this FC1, like, can anyone say like how many weights will be there? Like what will be the size of FC1? So maybe I can do it for you. So let's print the size of the weights of FC1. Yes. Yeah, so bias is being maintained as another variable here. Okay, sorry, it's self.fc1. Right, so it's 128, 784, and similarly for bias, it will be just 784. Sorry, 128. Okay, because for each neuron we will have one bias, right? So it will be 128. Similarly, you can print the weight for FC2, FC3, and so on. Now, in this network, the activation function is a ReLU. So ReLU means that it will take the maximum of 0 and whatever the input is it's seeing. Okay, and the forward is very simple. So whatever the input will be given to this network, it will reshape it. So remember, this X is a image; it's a 2D array. And right now we are considering a one-dimensional inputs. So that's why this image X is being flattened into a one-dimensional array here. And then we will apply the pass it through first fully connected layer, that is FC1. And whatever the output will be seen, that will be passed through the activation function. The activation function is ReLU here. Then this output of the first fully connected layer will then be serving as an input to the second layer. And this output here will then pass through the activation function, which will then serve as the input to the third layer. And the final will be the output, the model output here. So note here, we have not applied any activation function because this is the output we will be directly giving as an input to the loss function. Okay. And so this is simple model here. Now let's look at the data set. So again, this MNIST is available in the torch vision.dataset. So from it has been downloaded. Train equal true, make sure that we are using the training data for training part, and train equal to false results in those 10,000 images which are being kept assigned for testing purpose only. So this is the training process. It's very simple. I've kept it as simple as possible. We need a model, and this model is nothing but instantiation of this particular class defined here, which is a two hidden layer fully connected network. Then this optimizer is the so this is what we will be using to updating the model, right? So here SGT represents the stochastic gradient descent optimizer. You can try other optimizers which are available. Maybe you can try add a grade and so on. They all are available in PyTorch, and you can just change it here. Maybe I'll show one more experiment with Adam. Then this model.parameters is basically all the parameters of this model. So what will it will be? The weight and bias of FC1, the weight and bias of FC2, the weight and bias of FC3. So this is what model.parameters represent. So now to this optimizer, all these parameters will be passed and an initial learning rate. So this learning rate is what decides the step size, remember? So when we do this update in weight, it is W equal to W minus eta times of gradient of W, right? Gradient of loss function with respect to W. So this eta is this learning rate, which is 0.01, and the momentum value is 0.9 here. Loss function is this cross entropy loss. So what it makes sure that whatever is the right class, the probability of that right class getting predicted should be high. Okay. Now there are other couple of loss functions which are available in the library, and you can look at it. Maybe so many other, like you can pass it through sigmoid and then can do the negative log likelihood and so on, or you can pass it through softmax and do it. So a lot of there is. So this is cross entropy loss, in which it will apply the softmax first, and then it will apply this negative log likelihood function. Okay, so there are 10 epochs. So the training process here will go for 10 epochs. And how will it happen? This train loader is actually an iterator over this data set. It will generate the inputs as X and Y. X, the set of images, and Y, the true labels. This Y prediction equal to model of X will call this forward function of this class FC. So whatever the X we will pass, it will give you the output of this model. Okay. And this is, we are storing here as Y prediction. Sorry, here. So the loss will be pass this predicted value and the true value to the loss function. That will serve as a loss. We will use now optimizer. So we will make sure that its initial gradients is 0 before computing the new gradient. So optimizer.0 grade. And then this loss.backward will compute the gradients for each weight and bias term. And this optimizer.step will change or update these weight and biases according to this learning rate and the gradients computed using this backward function here. Now, once you keep on updating it for over the entire data set, we can look at its performance. So let's make it a bit more explainable. So let's print epoch. And accuracy. So epoch is basically the iteration on the dataset, the entire dataset we are talking about, and accuracy will be the number of images which are correctly classified by the total number of images present there. So that will be length of test loader dot dataset. Okay, am I printing somewhere shape here? So here you see that after 0th epoch, the accuracy was 90%. Then after one further epoch of update, the accuracy increased to 92%. And then it is increasing to 94% and so on. Okay, so the process is very simple. What we did is we needed a network which should be trained. So this FC defined this model for us. Then the second step was the data set, which was already available in the PyTorch version. So we directly loaded the data set. The third step is deciding the loss function. In this example, the cross entropy loss is used. It is a multi-class classification problem. And cross entropy loss is the best one. So it will first compute the softmax of the output, and then it will use this negative log likelihood term. So what will happen is that it will compute the softmax, and then it will make sure that the probability of the correct class is being maximized. And then there is this optimizer, which is deciding what should be the step size while updating these parameters and what should be the momentum. value. And once we have all these small building blocks ready, that is the model, the dataset, optimize and loss function, the training process is very simple. It's simply that you keep on iterating over the data points from the dataset and keep on predicting the model predictions, use the model predictions and the ground truth value, and you pass it through the loss function to compute the loss. So here loss represents how wrong is the model at present and in which direction it should be updated so that its performance improve, right? And this is being captured here by the loss function, and loss dot backward is giving the direction in which we have to update it. And here's this optimizer dot step, which is using this learning rate and the momentum value to update the parameters. This is the performance of the model after each epoch on the test data set. And you can see that after 10 epochs, the accuracy has been achieved by almost like 97%. If you want to visualize it, the results, I can do it for you. Just give me a second. And we can even visualize the results. So let's do it here. And instead of visualizing all, right now the batch size is very high. I think it is 128. So maybe we can just visualize 64 images. That should be okay. So I think that should be pretty good. So let's visualize only 64 images. So trace. So critical to make crate of X. Okay, and then let's visualize it. So the function is already written. I'll just call it and it will do the task. Maybe let's do it 16 right now. And let's also look at the values which the network predicted. Okay, so y prediction from 0:16, and let's do it only one iteration. Should be okay. Oops, I should have done it in the next cell so that it doesn't start the training again. It starts the training again. Okay, we have to wait a while, but I think you will see it maybe in a minute or so. It's very fast. In the meanwhile, any other questions you have regarding the network training part, or we can go over those? Yes. Yes, yes. Right. So that's a very good question, actually. So see, yeah. So you see here, this FC1 is a linear layer, right? So this linear layer is expecting a one-dimensional input, and the dimensionality of that one-dimensional input has to be 784. And the images which we are seeing here are 2D arrays. So that is the reason we have to flatten it to one-dimensional space. Yes. How can we compute the gradient of the network? I think that's what this backpropagation is doing, right? This is what I explained. You want another network which is a gradient of this network. I did not get your question. Can you please make it clear? Explain more. I see. Okay. Then in that case, whatever the loss function you are making, right? The loss function should capture it for you. So you have to define certain kind of loss function. So suppose in case of reinforcement learning, there is a model, okay? And your current model is using that model as the as a loss function, right? So maybe you can say that I don't know what problem it is, but let's consider a simple case. Suppose the model is F, okay? And the current model is G, and this G, whatever the output of G is coming, suppose G of X, that G of X is depending on the gradient of F of X. Okay, so the loss function should have some components. The loss function will be then depending on G of X and gradient of F of X. And that loss function will make sure that how you are combining these two things. See, whenever we are computing the gradient, what is playing the biggest role is your loss function, right? If you look here as well, this is the loss function which is making it possible to, so it is something which is providing some kind of function which you want to minimize, and accordingly you update these weights and biases. So if in your case your model output is depending on the gradient of another model output, then this loss function should capture that. And when you will try to minimize this loss function, you will be actually taking into account the gradient of the other function as well. Does this make sense? I think you can do it in PyTorch as well. So basically, when I'm doing here, right? Okay, I can show you something here. Just give me a second. Maybe after this, I can show you. So, okay, so this is how the input is, and I had to just do the Y prediction. So you can see, right? Most of them are classified 7, 2, 1, 0, 4, 1, 4, 9, 5, 9, 0, 6, 9, 0, 1, 5. I think it classified perfectly. Here you can look at other sets, so you can see some misclassifications. This looks too good. Um, but it makes sense, right? It is 97% accurate, so most of the classes will be correct. Maybe we can predict the classes for which it is not, images for which it is not doing right. So okay, maybe let's do it. Why is it coming a float tensor here? Okay, the problem is only one class got misclassified. Okay, so you can even look at the things where maybe I can do one more thing. I can increase the, and then we can expect at least 3 something. Okay, so here you can see that this 4 got misclassified as 2, 6, 0. So these are the cases in which the images got misclassified.